In this video, we're going to derive the Reynolds Transport Theorem. Which is often abbreviated as RTT. Now, why do we want to know this? This theorem allows us to shift perspectives, or to shift from a control volume perspective to a system perspective, and vice versa. So this is what lets us relate these two perspectives to each other. So to begin with, we are going to select an arbitrary piece of fluid and we'll do this at time t0, and we're going to select this fluid as both your control volume and your system. And just to remind you, your system is your collection of fluid particles. So here at time t is equal to t0, we have our, we'll draw our control volume in black, and we'll draw our system in blue. And initially at time t equals t0, these two are perfectly aligned with each other. So here I'm drawing an arbitrary shape to illustrate that these two are the same. And so we could say that at time t equal to t0, capital N of the system, and again this is at t0, is equal to capital N of your control volume, again at time t0. And just to remind you that capital N is an extensive property capital N is your extensive property. It could be mass or it could be momentum, and lowercase n is the corresponding intensive property. And again, the extensive property depends, this is one that depends on the amount of the substance that is present. The intensive property is one which does not depend on the amount of substance which is present. Okay, so at time t0, both the CV, the control volume, and the system are identical. They're exactly the same. Now, at some time later, so let's say that after some time delta t, the system has moved. So this is in a flow, the flow is moving. So the system has moved, but the control volume is still fixed. So the control volume has not moved. And we can draw that here. So at time t is equal to t0 plus delta t, our control volume looks the same. So drawing that in black as best I can to replicate what I did before. And then in blue, drawing our system has shifted somewhat. So it has maybe now moved over here. And so now this is our system. which has shifted, and in black is our control volume, which has not shifted. Okay, so what we're going to do here is we can divide up this system into 3 different regions. So we can divide up the system at time t0 plus delta t into 3 different regions. So we're going to divide this up into region 1 right here, region 2 right here, and region 3 right here. So let's think about those 3 different regions. So regions 1 and 2 make up your control volume. And regions 2 and 3 make up your system, this collection of particles that is moving throughout time and space. So we have this overlap where region 2 is the region where they both overlap. Region 3 is the fluid in the system that's exited the control volume. And so what we're going to do is we're going to come up with an expression for the amount of extensive property in the system at the second time point. So N of the system at times t0 plus delta t is equal to that property and the control volume at time t0 plus delta t minus the amount of that property in region region 1 at time t0 plus delta t plus the amount of that property in region 3 at that same time point. So t0 plus delta t. So essentially what we're saying here is that this first term corresponds to regions 1 plus 2. That's the control volume. That's regions 1 and 2. We're subtracting out region 1, and we're adding back in region 3. And so when we do this, we have simply regions 1 plus 2 minus 1 plus 3. And so that will end up giving us regions 2 plus 3, which is what makes up the system. Okay, now we want to know how this property N is changing with respect to time for the system. So we're going to write down the derivative here. So the rate of change of this extensive property N with respect to time for the system is, by definition, the derivative of the system, and here we're going to be using the material derivative, is equal to the limit as delta t approaches 0, so over some very, very small delta t, and the definition of this is simply N of the system at your second time point, t0 plus delta t minus N of the system at t0 divided by delta t, the time separation over which this occurs. So we have this expression for the derivative, and so what we can do is we can plug in this expression that we already developed for n of the system at time t naught plus delta t. So this expression right here, t naught plus delta t, is going to be substituted in down here. And we're also going to use another equation or another equivalence here, which is that n of the system at times t naught is equal to n of the control volume at t naught. So here we are taking this term and we're equating it to n of the control volume at time t naught. This makes sense because at t naught up here, the control volume and the system are identical, and so the extensive property of the control volume and the system are identical as well. So what we're going to do is we're going to plug those expressions in to our derivative here. So we have d of n of the system by dt is equal to the limit as delta t approaches 0. And here we're doing a little bit of rearranging on the fly, but we have n of the CV at times t naught plus delta t minus n of the CV at time t naught divided by delta t minus n of region 1 at t naught plus delta t divided by delta t plus n in region 3 at t naught plus delta t divided by delta t. So again here, just to illustrate a little bit of how I've rearranged this, this term goes right here, and the other three terms have come from this expression up here. So these have contributed to these expressions, and here's the other term right there. So that's where those three terms have come from, and n of the CV at t naught has come from where I've marked in green here. Okay, so we have these three different terms, and we're going to mark those as terms 1, 2, and 3. Okay, and we'll look at those individually. Okay, so in the limit, the first term or term 1, so we have the limit as delta t approaches 0 of n of the control volume at time t naught plus delta t minus n of the control volume at time t naught divided by delta t. Well, we can recognize this as simply the derivative. So this becomes, here we have the partial derivative of n of the control volume, so d of that by delta t, and this can be rewritten as del by del t of, in parentheses here, I'm going to write the definition of the extensive property of that control volume. So we have the integral over the control volume of the density of the fluid times the lowercase n, which is the intensive amount or the intensive property, integrated over some volume. And so what this term represents is This represents the time rate of change of your extensive property N within the control volume. So for example, if you had some fluid accumulating within your control volume, maybe your control volume is a large tank and you have fluid accumulating in that control volume, then this term would represent that. So this is the first term. Now we're going to skip to the third term. So this is the third term. The second and third term are quite similar. And we're going to look at the third term because it's a bit easier to understand. So the third term here is in region 3 at time t0 plus delta t divided by delta t. Now what does this term represent? This term represents the rate at which your property N flows out of your control volume across the control surface at this region 3. And so we can see that graphically, right? So if we look back up here at our chart here, we can see that region 3 here sort of represents the flow that's exiting the control volume, and sort of the size of region 3 represents how much is exiting or has exited over some amount of time. And so we're going to call this term in dot out. So this represents the rate at which your extensive property is flowing out of the control volume. So we want to come up with a more tractable expression for this term. And in order to do that, we first need to know the rate at which the fluid exits the control surface at this region 3. Right, because the fluid is exiting across the control surface, and the fluid is carrying this extensive property across the control surface. So first we need to know how much of the fluid is crossing that control surface, and then we can figure out how much of your extensive property N is exiting with the fluid. And so to do this, we're going to draw a little diagram here to represent this. So this could just be flow in a channel where we have, let's say this is our control surface representing 3, and we have some velocity in this channel which is exiting across this control surface, which has a velocity of v3, let's say. So we have this uniform flow profile across the channel, and it's exiting across some area which we'll call A3. Okay, so we can look at the volume of fluid which is crossing this control surface. Again, your control surface is this right here, this line right here, this dotted line, and the volume of the fluid which is crossing this surface 3 in some amount of time delta t is given by, so we're going to say this delta v3, where again the cross mark through the v indicates volume. So this is a volume. So this is some differential or elemental volume that is crossing this control surface, and we find that this is just equal to the velocity crossing over there. So the velocity of 3. Do this in black here. So this is equal to the velocity at 3 multiplied by the time over which this occurs, multiplied by the area of 3. So this velocity multiplied by time gives you units of dimensions of length. Length multiplied by area gives you dimensions of volume. So this is a volume that's crossing this surface. So just to illustrate this a little bit better, we have dimensions of length per time multiplied by time, and then multiplied by length squared, and this gives us length cubed. So that gives us the volume of the fluid which is crossing this surface in the amount of time delta t. So that's the fluid crossing, but that's not necessarily the amount of the extensive property which is crossing. So the amount of capital N, your extensive property, which is exiting this surface, is the amount per unit volume, the amount of N per unit volume, which is rho times lowercase n times this volume that we just found. So the volume delta V3. And so we can write this expression in 3 at time t naught plus delta t is equal to this rho times lowercase n, and again, rho is mass per length cubed. N is the amount of your extensive, lowercase n is the amount of extensive property divided by the mass, so that's your intensive property. And so this becomes, you multiply this by this elemental amount of volume of fluid, and this becomes rho times n times A3 V3 delta t. So that's the amount of the extensive property n at time t naught plus delta t. That's crossing this surface. And so this is the amount that is crossing, and so then the rate at which this is crossing can be found by taking the limit as delta t goes to 0 of this expression, so in 3 t naught plus delta t over delta t, and this becomes rho in A3 V3. So this is the rate at which your extensive property is crossing that boundary or that control surface. And that is for surface 3, which is for fluid and that property exiting your control volume. Now you can do the same analysis. for your second term. We're not going to go through that, but you'll end up with a very similar result, which you'll find that the rate at which this extensive property is entering or is coming in is equal to rho in A1 V1. So we have expressions for our first term, our third term, and our second term, and now we're going to put it all back together. So the rate of change of our extensive property of the system is equal to the derivative of the extensive property in the control volume plus the rate at which it's exiting, that property is exiting, minus the rate at which this property is entering. This is equation 414 in your textbook for reference. And this is a statement of Reynolds Transport Theorem. We can rewrite this as well. I'll rewrite this one more way. So the derivative of this property in your system is equal to the derivative of the property in the control volume, del NCV by del T, plus rho A2 V2 into minus rho A1 V1 N1. And the way I've written it here, this is an expression for the Reynolds Transport Theorem for a fixed control volume, so control volume that's not moving, and one that has only one inlet and one outlet. So this is a general expression for the Reynolds Transport Theorem. Again, the purpose here is to relate the system approach, which you can see we have the extensive property of the system on the left-hand side with the control volume approach. And so we have the control volume on the right-hand side. So again, this is a way to shift back and forth between these two reference frames, which we often need to do in fluid mechanics. So this is a very generalized statement of Reynolds Transport Theorem, but we're going to try to generalize this a little bit more to make it applicable to more situations. For instance, the control volume might be moving, or we might have more than one inlet and more than one outlet. And so that's our next step, is to generalize. So we can generalize to a control volume with multiple inlets or outlets. So that's one point we can do. And where flow across the control surface is not perpendicular. So in our previous example, we had flow going across this control surface right here, and this flow is moving across perpendicular to that surface, which makes our analysis quite simple. But that may not always be the case. And so we're going to extend our previous result to take into account a case where the flow is not going to be perpendicular across that surface. So I'm going to draw a control volume or a control surface here, sort of in 3D. So this is a control surface that I've drawn. The interior of that is a control volume. And on this control surface, we have a little patch which we're going to be looking at or examining here, and we're going to call that patch delta A. So this is delta A. It's some elemental patch, elemental area that the fluid is flowing through. Now the direction or the direction or the orientation of this patch is defined by a unit vector which points outward, and that is called in hat. So this is an outward unit vector. Make it a little bit neater. In hat, this is an outward unit vector which defines the orientation of that surface. And each point on the surface has this unit vector pointing outwards, defining its orientation. So that is the unit. That's the unit vector. It's perpendicular to the surface, but flow is not necessarily moving perpendicular to your control surface. In fact, in this case, we're going to have flow which is represented by this vector v. This is your flow vector, your velocity vector. And it's not perpendicular to your surface. In fact, there's some angle, which we'll call theta, between these two vectors. So now we need to revisit this question of how much fluid is passing through our little patch, delta A, in our time delta t, and then how much of your extensive property n is flowing through as well. And so we can write down an equation for delta v. So this is going to be v cosine of theta delta t delta A. And just to remind you, this is the volume of the fluid which is passing through our little elemental region, delta A, this area, in time delta t. So again, volume of fluid, you basically take v cosine of theta, that's the amount of v that's lying along your vector n, and then you multiply that by the area, delta A, and the time, and that gives you the volume of fluid which is passing through this area in time delta t. Following the steps we did before, delta n is equal to rho n delta v, which expands to become rho n of v cosine theta delta t delta A, which is the amount of your extensive property n passing through your area delta A in time delta t. Now the rate at which this is occurring is rho in v cosine of theta delta A. Okay, now, so this is over a very small area, right? This is over delta A. We want to know not just what flow is going through delta A, but really what flow is going through the entire control surface. And so what we can do is we can integrate over the entire outflow region and this gives us a rate in dot out is equal to this integral over the control surface where the flow is going out of rho in V cosine of theta dA. Now there's one more way to write this using vector calculus, which is convenient, and we will often do this. We can write this as the integral over the outward control surface of rho in V dot n. So we have the dot product between your velocity vector and n hat, your unit vector. And just to remind you that this expression V dot n hat is equal to V cosine theta. So we'll often use this vector calculus expression instead. So this is now integrating over the entire outflow portion, but it turns out we can further extend that integral to include both the outflow portion as well as the surfaces where the flow is crossing into the control volume. So we can extend the integral over the entire surface to include both inflows as well as outflows, as well as areas where no flow is crossing. And the reason we can do this, we can write this term as the integral over the control surface of rho in V dot n hat dA, as I wrote that before. But the nice thing about this, and the reason we can write this over the entire surface, is that this expression V dot n hat, which equals V cosine theta, again, that's the component of V lying along the unit vector. This term is going to be positive for whenever you have an outflow. It's going to be negative for whenever flow is moving into the control volume. And it's going to be 0 for no flow regions. So for example, along a pipe wall where there's no flow crossing, this term would be, this term would be 0. And so rewriting everything together for this final version of the Reynolds Transport Theorem, we have the derivative of the system, the derivative of this extensive property of the system is equal to del by del t of the integral over the control volume of rho in dV plus the integral over the control surface of rho in V dot n hat dA. So this is the final version that we'll be looking at further. And just to, again, provide some perspective about what this means in words, this means the time rate of change of the extensive property capital N for a system, again, for a system is a collection of fluid particles. So the time rate of change of some property for the system is equal to the time rate of accumulation of capital N, your extensive property, in the control volume that's the first term on the right-hand side, plus the amount of gain minus loss of the extensive property N through the control surface. So this is a statement of the Reynolds Transport Theorem that we have just derived.